check.
So do you have empty pocket? Keep it in back.
Okay.
Yeah.
Oh, okay. Oh, okay, good. And pointer. Okay, good. Okay, okay. In case I need to.
Hello everyone. Welcome to ISTS weekly string seminar. Today we have Justin David. He will tell us about thermal one-point functions in holography and large N models. Please.
Okay. Thank you. Yeah, I'm very happy to be here. It's I think after COVID, I'm here for the first time giving a talk. I gave a talk here through COVID times, I think, and it's good to meet everybody. So I'll be talking about this work, thermal one-point functions, done with a student who's also attending. So he works with me, and he's an ISC, and it's based on these two papers. So let me sort of begin with a simple introduction so that we know what we are doing or what we are heading towards. So we are considering a conformal field theory at finite temperature. So it's on S1 times. So the spatial extent is basically this, the real space, d minus 1. So the conformal field theory is in d dimensions, and the finite temperature is reflected by the fact that it is compact. S1 is compact. So on general grounds, if you look at an operator of dimension delta, it acquires an expectation value because of scaling t to the power delta times a number. Now this number BO, so I've extracted all the scale out of it because of this temperature. So this number can be a constant, it's a constant, and in fact, because of translational invariance, it's actually independent of position of the insertion of the operator. And this number can depend on the operator itself and the details of the conformal field theory. So so what we are basically interested in studying the property of that number in a class of operators as well as in a class of theories, and to see if it has interesting properties. So that is the question. So are there universal properties of this constant which determines the expectation value of that operator? And a simple way, if you ask such a question, and now that you have a tool of ADS-CFT, it's first thing one can do is just look at the theories which admit gravitational dual. And if you look at that, you get a class of theories, right? And because they all tend towards this gravitational dual, then one can study this simple question that way, right? So a class of conformal field theories is known to admit ADS duals. And in this dual description, black holes in ADS are dual to CFTs at finite temperature. So you remember, you're interested in the CFT at finite temperature, so we look at the black hole in ADS. And one way of...
Justin, I have a question.
Yes, go ahead.
Yes, so, I mean, the one-point function is expectation value of some OX, right?
Some OX.
Of X.
Yeah.
So, why is it independent of X?
Yeah, so because of translation invariance, in RD minus 1, you can show that it is independent of X. So you just say insert a P operator and take it across, and you can show that the derivative of this fellow is 0, and so it's independent of the position X, where you insert
But
it.
it seems to be manifestly dependent on X. I mean, OX expectation value of OX seems to be manifestly dependent on X.
How? Let's look at OX on a vacuum itself. I mean, a simple thing like that.
Yeah, vacuum expectation value. Take the vacuum expectation value of OX.
Yeah. So why should it depend?
How is it
So, yeah,
independent
imagine
of X?
inserting a momentum operator on the vacuum, take it across using the commutation relations of the momentum and O. That will be the derivative, of that expectation value with respect to X. And
Yes.
but P on the vacuum is 0, and using that, the derivative of this expectation value is 0. So it's a constant. It's some elementary thing in quantum field theory, actually. Yeah, I'll go ahead. Yeah, so
Okay.
so we can evaluate this one-point functions of field dual to operator of insert using rules of ADSCVT. Because as I said that, okay, suppose we are naively interested in some universal properties, let's just look at holography first. Then there's another way of studying this question. If you have handles with you, like, if you have solvable models like the ON model or the UN Gross-Neveu model, these are solvable models in large N limits. And one can study, thermal one-point functions of certain classes of operators like bilinears in large N, as well as a strong coupling using a certain formula which was recently, not very recently, but introduced in the literature. So we will, do both in this talk if I have time. So first, I will go to one-point functions in holography. So this was actually, it was a talk by Maldacena which got me into this. Maldacena and Grinberg in 2020 studied this question of one-point functions in holography. And they argued that taking large conformal dimensions, because conformal dimensions are related to the mass of the scalar field, as you will see in a particular way, we will see that in detail. One can read out certain features of the interior geometry of the black hole from these one-point functions. That, of course, looks quite interesting. So, and the structure they see is the following. One-point function goes as exponential of phase, where this tau s is the proper time to the singularity. Okay, so you have imagine you have a structure like this, a black hole, and there's a singularity, and there is a proper time here. I will draw a picture again, and then there's a boundary because we are in the we are in ADS-CFT, and then there's a spatial distance here, which is L hor. Right. So these two lengths appear in the one-point function, okay, under particular scalings and so on. Okay, we will see it explicitly because we'll go through this in a little bit more general way. So this is tau s, yeah. Yeah, horizon to the singularity. So you drop a particle here at 0 energy and just let it go inside, and then you calculate that time. From from here. Yeah. So this is the structure they sort of say the one-point functions have. Yes.
This number basically just depends on the temperature.
This depends. No, in this ADS case, it depends on the radius of ADS and the dimension you're looking at. For ADS black holes, black holes. Yes, and dimension. Dimension of the space, d. And the radius of ADS in this particular, in the flat black hole case, it depends on the mass, but in this case, it just depends on the radius and radius to 1. So it's 1 by d or something. Yeah. That it is not sensitive to that. Yeah, it is. Yeah, it's surprising. I'll show it. I'll show the calculation. Yeah. Oh yeah, so I can tell about the angular. We tried to do the angular momentum. We will do the charged black hole. Angular momentum, yeah, we didn't have very much success. Yeah.
So what I'm trying to understand is
yeah. It's one number. Yes, so I check it for say black holes with hyperbolic horizons. So there it's a different dependence. So there also we can check indeed. It's a different dependence from ADS. So let me go ahead and you will see the structure emerging actually. Yeah.
Justin, I have a question.
Yes.
So in general, when you're computing 2-point functions, if you have the proper time, then it's usually you compute the path integral over all possible e to the IMTSs, right?
Right. So here, for instance, the way we are computing this 1-point function is using, as I'll go ahead, is using the rules of ADS-CFT.
Okay. But even if you use ADS-CFT, what will change is instead of a flat metric, you would have the ADS metric. That's all that will change.
Yeah, and you have.
And I mean, in the flat metric, you get a Bessel function, k Bessel function times something. I mean, it's not e to the IMTS, just e to the minus IMTS, where TS is the proper time.
Yeah, so maybe we can ask this question when I do the calculation. So
okay, fine.
Yes, yeah. Hor, yeah. Yeah, which I will tell you how to do the regularization. I'll tell how to do that. Yeah. So this Malderson and Grinberg had an exact calculation for the planar Schwarzschild black hole. Then they had a specific kind of WKB analysis for black holes with spherical horizons, ADS4, ADS5. And in fact, they had a charged black holes only in ADS5. But all this was a WKB analysis, which was quite, at least to me, it was a little obscure. It involved complex radial positions and justifying certain locations of the saddle in the WKB. Right. So what we will do is we will try to, we will revisit this exact calculation, and we will see how far we can do exact calculations in the other cases. Okay. So we will revisit this, and slightly generalize the Malderson and Grinberg's calculation for the planar Schwarzschild black hole, and then present exact calculation for the planar charged black holes and in a suitable large D limit, black holes with hyperbolic horizons. So these are the two examples, and in both cases, the 1-point functions assume similar structures. Okay, and in fact, the calculation demonstrates that, as you will see from the calculation, it relies entirely on the geometry outside the horizon. Okay. So that is also interesting. So let's just proceed with this Malderson and Grinberg calculation. So a conformal primary is, of course, the dual to a minimally coupled scalar of mass m, and this is the dictionary. I think everybody in the audience knows this. And to induce expectation value of 1-point functions, they consider the minimally coupled scalar, right, with this Weyl tensor squared, right? Because just this is, this does not have 1-point functions. So they introduce this higher derivative coupling to the minimally coupled scalar. Okay. And the scalar, of course, this couple, they chose the Weyl. I will give you the reason for the Weyl tensor squared coupling. But you can see immediately, because it's a higher derivative coupling, and in terms of ADS5, if you see, it actually is suppressed by the Tuft coupling. Okay, so it is certainly, it's the next order, basically, calculation. So they argued that these couplings of higher derivative couplings are always present because, you have 3-point functions of this kind, T, T, O, right? In the CFT, you have this by Ward identities, you can get this. And because this is non-zero, such couplings are always present. Okay? They argued for such things. And because of and they said that it has to be the Weyl tensor because, in vacuum, there's no such expectation values. But at finite temperature, there is. And Weyl tensor, in fact, for the pure ADS vanishes. Therefore, it is sort of it picks out the fact that you're in a black hole. So they argued for this Weyl tensor. But we know in general, yes, yeah. Yeah, so this 3-point function in CFT is not 0.
This ordinary coupling give you also 3-point function of minimal coupling of matter.
Mini couple. So how would, like, there is always 2 phi's here.
No, I think he's asking 5 times R will also give you
5 times R.
Yeah. So
Yeah.
but that is
Yeah.
Square root G has it.
Yeah. Square
So
root.
square root G you get.
Square root G. But this is quadratic. This is quadratic.
He's not saying that there are no other
Yeah.
contributions to TTO.
Yeah.
He's saying that there will be a y square contribution to TTO.
Yeah.
And so that coupling would be present. And
Yeah.
that's the only
Coupling.
that can make a difference to the 1-point
Function.
I see.
Yeah.
So phi R will also give you this thing, but
Yeah.
But it wouldn't.
It wouldn't, yeah.
It wouldn't contribute to the
1-point function.
And the 1-point function only something that
Yeah.
vanishes in the pure ADS, but doesn't vanish.
Yeah.
in
But
ADS.
yeah. So that's.
R minus D, O of R minus whatever constant it is in
Yeah, so I will come. I'm going to address that soon. Yeah, just hold on. So this is their argument. They say that the Weyl tensor vanishes for MTDS, but it's non-zero. But we know, and we will see the mechanism. We'll know that such couplings are what is generally present. I mean, this is present in string compactification. Phi times the Gauss-Bonnet couplings, right? And the question is that whether the Weyl tensor squared coupling and this Gauss-Bonnet have similar features. And we'll see that the constant thing which you mentioned comes in. So our results of thermal 1-point functions. Yeah, that's the scalar minimally coupled, which that's such such couplings are present in sort of generically. Yeah. So the question is that, and in fact, I think the way we got in, because I knew that there are entropy calculations which are invariant if you do the Weyl tensor squared coupling as well as this. Okay. So that's their argument. So let's go ahead with this one. And so using the rules of ADS CFT, the Gauss-Bonnet, we will proceed with Gauss-Bonnet actually. And I will show how it relates to the Weyl tensor squared, right? So using the rules of ADS CFT, this is the computation one has to do. We have a bulk boundary Green's function. We fold that with this, the Gauss-Bonnet thing and do this particular integral. So this is the simple, this is what the rules of ADS CFT says to do. And the range of integration here is actually like, the range of integration is over the ADS Schwarzschild black hole, which is essentially exterior to this. So it is the integral runs from the horizon to infinity and Euclidean calculation. So one imagines it's a Euclidean and then you just do this calculation. This is the metric of the planar Schwarzschild black hole. Here it is, this is the blackening factor. I think some people are familiar with, this is quite familiar. Now the Gauss-Bonnet curvature term is the following. So you see that there is this term which depends on the temperature. You can see that 1 by Z naught is proportional to temperature to power. And then there is this extra term. Okay. It is 1 over root lambda. In ADS 5, for instance, you can convert that to, because there is a string coupling in front, because there's a higher derivative term. Yeah. So it's not, you have to go a little bit beyond the, lambda is equal to infinity to see this. At least from ADS CFT point of view. Yeah. Yeah. Why? Yeah. Yeah. Well, yeah. Such, of course, certainly such terms are there. And yeah.
Like for instance,
yeah.
There's a relationship between an EDS primary operator and some field in the
right.
Which arises in some mass.
Yeah.
Maybe that in itself corrected.
Yeah, but if at all it gets corrected, it will feed in at a higher order here, right?
Are you saying that
yeah.
Yeah.
It just comes to field.
But how do you know that phi, the correct field you should be using the bulk is phi minus?
Yeah, but that will also come at higher order, no? Yeah. First, yeah.
non-zero term. So anything will be.
Yeah. Because there is a 1 over root lambda sitting outside this.
It has a 1-point function. If I phi minus metric by lambda, then the metric something going to metric has a 1-point function.
Yeah.
Isn't that maybe something which you're saying?
Yeah. I don't know what I have to see. Yeah, that one. If at all it's going to spoil this. Yeah, I don't know. Yeah. 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 Dimension. Yeah.
You're saying that phi minus something into phi square would equal to everything would have some 1-point function of this 1 by lambda. So if I do any kind of direction, then
Higher order. Okay. So here, yeah. Now you see the difference. So the Gauss-Bonnet term is this following. Okay. So there are two terms here. You see, there is a constant. It doesn't matter what the constant. This is a constant, and then there is this extra term. And the Weyl tensor is actually just this. Okay. So the Gauss-Bonnet and the Weyl tensor square in this background at least differs only by this. This is the temperature-dependent term, and this is the constant. This is the constant, right? So the additional constant does not contribute to the 1-point function, as you will see soon in the calculation. Okay. Okay, again, go back. The metric is translational invariant in T and X. And in fact, going through a careful analysis, you can convince yourself this is also independent of T and X. And the constant mode can be extracted by solving the bulk boundary Green's function at 0 frequency and 0 momentum. Okay. And so, therefore, the only radial dependence is important in this. And once you solve the bulk Green's function, this is a strategy to extract out the bulk boundary. You solve the bulk Green's function and just use this rule to extract out the bulk boundary Green's function. Yes.
This extra term, which is this constant.
Yeah.
Is this a more reverse phenomena, or just this particular case?
This particular case, but it also will show that any constant will not contribute to the 1-point function. This calculation will show that actually that this is a particular constant in this case, but it will show that this any constant.
The difference between the Gauss-Bonnet and the Weyl curvature, being the constant is actually a consequence of the metric, right? This metric you take planar short shell black hole.
Right, yeah.
But if you take something else, then it might not be the case. The difference is constant.
It might not be. I mean, that's a different background altogether. We are looking at this particular.
On-shell, since they are related by field
definitions.
On-shell, when you evaluate it, it probably can only depend by a constant, because it can't depend on anything that when you do a variation, it shouldn't. You should be able to argue that way. That
you mean this term is not there? I mean, this temperature.
That term is there.
Dependent term,
but since
related by field
redefinition, and field redefinition doesn't change the equation
of motion, yes.
Right. So if you put back into the on-shell action,
right, then it will just at the best
depend by something which doesn't depend on
the background. Yes, right,
The argument for the 1-point function not depending on which
no, but even for the Lagrange, even for the action, action for this is the
geometry. This is for
action is being evaluated
on shell.
So this is being evaluated on a solution of the equation. If,
for
instance, it had a piece that depended on Z0, then you would say that
then there will be how can you redefine your fields to get the same right.
It should have affected the equations
of motion.
Since the equations of motion. I mean, it's not a precise argument, but it makes sense.
But here, we will show explicitly these constants don't. I mean, and it also solves the problem that if you add a constant times phi, I mean, it won't have a non-trivial expectation.
The claim seems to be actually something which I'm finding a little strong. Maybe it seems to be given the TTO vacuum expectation value.
Right.
I can actually predict the thermal expectation 1-point function of O. And there's some robust relationship between them in a strongly coupled CFT. That seems to be the claim, right? Because I'm given TTO in the vacuum. From that, I can predict I can say in any strongly coupled CFT with a holographic dual, I can get 1-point function of O.
Yeah. Yeah. Yeah.
Is it
Yeah.
true that
There's
you
an
can get the
OPE,
1-point function of O at finite temperature
Yeah.
given TT or vacuum?
Yeah. Yeah.
Might dominate. I mean, this is some. Good. But then if there's such an argument, one should be able to get it directly without going through bulk effective field theory. You're saying without going through bulk effective field theory, using TTO at vacuum, I can get expectation of thermal expectation of O in at finite temperature. No, I think you have to use the fact that something like the thermal block.
Yeah, you have to use the thermal block, some kind of large C kind of blocks that we used. Yeah.
So there's a thermal block expansion.
Yeah.
1-point function can be expanded in terms of O pi phi, sum over phi. Pi is in the thermal block, correct.
Yeah.
That's right. That's right. That's right. Good.
So if you want only the OTT to dominate,
Good.
you should argue that OTT contribution dominates in some large C or something.
Over other things.
All other things.
Yeah.
And then it will be proportional to OTT.
Yeah.
Very good. And then it'll
But
be
in that case, you should be able to do that calculation without using ADS.
without using the bulk.
Yeah, if you know the thermal blocks at all very well and how to take the large C limit. Yeah, I don't know. Yeah. In fact, the second part of it is a little bit closer to that, as you will see, actually. Yeah.
And this is a reasonable statement that only the TE dominates over other things that might run in the thermal expectation.
Yeah. Yeah, usually the stress tensor block dominates, in the large C. Okay, let's see the calculation. Yeah.
Justin, I have a question.
Yeah, good. Yeah.
Like, when you have the scalar coupled to the gravity system, shouldn't the solutions, shouldn't the metric, for instance, depend on, the total equations of motion concerning the scalar as well as gravity? This seems to be a solution of just the gravity part.
Yeah, so this is the background, and then the rule, to find 1-point functions or even 2-point functions, for instance, what you are instructed to do is to, substitute the bulk boundary Green's functions wherever the scalar occurs and perform the, bulk integrals.
This is a consistent solution of the full fraction.
Yeah, it's consistent, yeah.
Also, the field phi is not as massive
as the full, it's not back reacting.
I see. Okay.
Sorry,
yes, go ahead.
Yeah. This thing of T dominating, you're trying to compute trace of e to the minus beta h of O, which you write as sum of e to the minus beta h n o n, and that turns into a 3-point function.
Okay.
However, the states that dominate in the thermal trace are of very high dimension because the black hole is very high dimension. So to say that the OTT will dominate the expectation value, it seems to be very strange at finite temperature, right? If you said O and very heavy primary operator, very heavy primary.
You're expanding around the thermal line. You're not expanding around the original line.
Yeah.
That's what the thermal block
Is. Yeah.
So you say that I should then look at OTT about the
Okay.
I think that's probably what we do for the thermal block.
Yeah, for the thermal block, that is a little bit more exact. There I know we'll see how to do that. Yeah. So this is the differential equation, which we need to solve the bulk Green's function in the zero frequency sort of limit, because we are in the constant mode, and the uniform expectation value can be done once you solve for the G. You just substitute and do this integral. And you see the integral is from Z is the inverse, so it's going from the horizon to infinity. Z is like 1 by R, horizon to infinity. So we do this integral. And the differential equation is exactly solvable. I think this was noticed that it was solvable, even though it was it was solvable in a nice way by Myers first. Myers and company, there was a paper. So it's solvable, and it's some hypergeometric function. You can plug in and do this integral. Now this is the extra constant. For the bulk Green's function. So in the black hole background, in some limit or exactly. Exactly, but at zero frequency and zero momentum. because that's what you need to extract the constant value. So, if you want to extract,
you said it's solvable. That is solvable
only in the zero frequency. And because if you take the general one for arbitrary frequency and all, it's some human function, and it's not. It's very special. I mean, it just happens that it's solvable for that particular case. So so there is the solution, and now I have plugged this back inside, and there are the two terms. One of them was the temperature dependent term, and one is the one which was independent, just a constant. And if you integrate it, actually you can use certain integrals, and this one, when h minus 2, so this guy, like h plus n, and when n is equal to minus 2, it vanishes. I mean, that constant term, actually, that integral vanishes because there is a gamma function downstairs. So the constant does not contribute to this expectation value, and it's only from here, and it is some value like this, no? So the thing Maldacena does is basically takes the large h limit in a particular way, and this is sort of the signature he's looking for the time to singularity. So this is that, and here there is some structures to it. Okay, so this is the answer, so as I said, that the Gauss-Bonnet coupling answer is the same as the Weyl tensor answer. Now, if you take this h going to infinity minus I epsilon, so he wants to take the minus I epsilon because this 1 by sine pi h thing is like e to the power of I pi h and e to the power of minus I h pi h, and one wants to isolate e to the power of minus. You can isolate the other one also, but you want to isolate one such term. That is this e to the power of minus pi I h, and from this term, when you take the large h limit, you get 2 to the power minus 2h, right? So you get these terms, but you can very well keep the 1 by sine pi h as it is.
H was the
h was delta by d, right? And we are taking large h limit, and so that's the answer. Right, h is, we are taking, in fact, okay, so here that is an important, we are actually doing analytic continuation. If you look at this integral, if you think about it, expansion around w is equal to 0 or w equals 1, if you do this, it is good for small h. I mean, it's like you have to do the integral, get this answer, and then push it to h, going to infinity. If you look at the integral just like that and just try to do it, so there is an analytical continuation here, actually, which is going on. So this answer is known exactly, right? And then you push. This integral naively, if you look at the integral, it diverges. So the integral is done and then pushed to h goes to infinity.
Large h, can we just ignore the back reaction and think of all these things? Because we are ignoring the back reaction, right? Large h is like a large mass thing, right?
Okay, yeah.
So we're still ignoring the mass.
Right. We are still treating that, just like that. We are analytically continuing this, No, because you see w to the h. So let's look at this. I think this Taylor series expansion, w to the h. Like, if I want to integrate this, let's do it like, 1 minus w. I think w goes to 1 if you look at this expansion, or like you write this as 1 minus w to the h. And you write this as w, right? You write this as, because the integral is same, 0 to 1, dw. And you do this close to 1. Close to 0, it is okay. But close to 1, I think it is not quite good, actually. There will be a w to the power minus some, 1 minus 2h or something coming out when, when you actually expand it close to, I don't know, I have to remember now, actually.
Normally, if there is a divergence, even the function is negative argument.
Right. But I do think, okay, maybe I'm not able to reproduce this now. I mean, but I don't think it is naively if you just do it with arbitrary large powers of h. It's convergent actually. So I don't remember. But it depends on the hypergeometric function. If it has like w to the power minus, see, I think it has w to the power minus 2h behavior at some place. I mean, maybe at close to the origin. You have to see how the hypergeometric function behaves, right? So.
You should have gotten gamma function in negative order.
Yeah. Well, yeah. That this is the answer. Yeah. It cancels. Yeah, it could be. Yeah.
The thing that works for me is that if it diverges really and it doesn't cancel,
yeah.
the way you interpret this is that if there's no parameter here except for h.
H.
Think of this expectation value
Yeah.
as a function of h.
Yeah.
And provided you integrate it to the smooth function as a distribution,
Yeah.
you should use the right answer.
Yeah.
There's no sense in which you should think of the expectation value of the primary as a distribution over the dimension.
Okay.
I mean, if there was some other parameter like
right.
something, it would make sense.
Yeah.
Here one is really saying that think of the expectation value as think of some superposition of primaries with different dimension, and then this is the right.
No, but maybe
the sum is finite.
Yeah.
The sum might be finite. Something the individual terms.
Then there should be a hypergeometric identity that lets you.
Yeah. It's an identity. This is an identity.
No, that lets you write the integrand in a form that makes the
Yeah. Yeah, maybe, yeah. But this is the answer from Grafstein. Yeah, it'll give you this because the computer knows these identities. Yeah. So, and this is the domain. Here it is, yeah.
Oh, but maybe the point that they're making is to use that sum of hypergeometries. But if you go to the previous slide.
That is finite. That cancels the
second one, write it as a different hypergeometry. So that
the
integrand becomes finite for all.
Yeah.
The integral is really finite for all.
Yeah.
That seems to be the second one.
No, second one is actually like, this is the one which we did for the Gauss-Bonnet. This is the extra term due to the Gauss-Bonnet. And this is h minus 2. Right? So h minus 2, if you look at that, this has like n equals minus 2 here. And that vanishes. That vanishes. Yeah, negative. Yeah. Yeah. So it's actually this answer, in fact, they clearly mention it. I mean, this answer is taken and it's analytically continued. Analytically continued.
But you have gamma of h plus 1 and gamma of minus h plus 1.
Gamma of
n equal to 0.
N equals minus 2, yeah.
Or n equals
minus 2, yeah.
Okay, but probably the cosec is coming from that identity, right? Gamma
The cosec is coming from the identity. It's coming from that identity.
So if you use that, then it is finite if h is not an integer.
Right, yeah. I mean, if that is, that's...
if h is an integer, then of course the cosec
itself diverges,
But if h is not an integer, then I don't see any problem for large h with this answer.
Yeah, it's, I guess, it's...
The integral problem is divergent, otherwise you wouldn't get gamma of
minus h plus...
So it's an analytic
continuation. That's what, it's analytic continuation. I mean, it's just like, So we do this and we get this result.
Justin, I have another question. This is a very naive and fundamental question. Like, are you saying that ultimately the one-point function will still be independent of position?
Yeah, that's what we have seen here.
Okay, fine. Now the question is, like in the presence of the black hole, the translation invariance is broken, right, of the vacuum.
This is a planar black hole, and we have translation invariance in x and t.
Planar black hole. I mean, in presence of the black hole, the translation invariance of the space-time is broken.
Yeah, that's the z direction.
I see. Okay, so in space-time, you mean on the boundary theory? I see. Okay.
So this is the result, and now let us just take this. We keep this answer. Yeah.
Is there if I do denormalization, like holographic denormalization?
Okay.
I have to remove this element.
Yeah. Yeah.
Could it be that the answer will be 0 rather than this element?
Zero.
The thing is, if you add the right local boundary
terms, this would be the answer. Yeah, this finite term. Yeah. Yeah. I don't know. Yeah. 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 Why it is? Yeah. 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 Okay. So. Yeah, thermal 1 pi. It's those are non. It's yeah. It has. It has. Okay, I've not kept it, but you know, if you look at all this, yeah, I've not kept it, but it depends on the temperature correctly. Yeah. Yeah, I've not put it actually. Sorry, I've actually set. Yeah, I've set it to 1. Yeah. Yeah. Here, for instance. Yeah. Yeah. Okay. Good.
In fact, it's a power.
Yeah. So yeah, Z naught. Yeah. 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 And this is the coefficient. I mean, yeah. You can't. Yeah. No. I think. Yeah. Yeah. Okay. Yeah. Okay. So now let's look at proper time. Okay. So we consider radially infalling geodesic with 0 energy released here, and you know this is just this is a simple classical mechanics problem, and you can calculate the time to singularity, and here it is. It doesn't depend on the mass. I mean, it just depends on the radius of ADS and the d. So that's the time to singularity for this ADS black holes. And so this is a regularization they seem to do, but let's do that. I mean, so look at, you know, of course, this is infinity. I mean, this is the boundary, and to the horizon, we are doing the integral, the spatial integral, the proper length, and we put a cutoff, and here there is this log L epsilon by Z naught. We keep the finite term. Now, so that is L hard, and if you look at this expression, right? If you look at this expression, that is precisely that structure, minus Im tau s minus ml har. Yeah.
The real part would be different if you use the reference scheme again in geodesic.
The real part would, yeah, the real part is actually not particularly, yeah, something very, yeah, but we keep the, we have done it for many other examples, no, and we keep the same scheme and similar structure. The structure is the same actually. Yeah, the real part is not so. Yeah. 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 Huh? Yeah, this is 2 to the power. This is 2 to the power. I mean, e to the power of minus m r, you know, by log 2, log 4. Yeah.
But that seems to be that's not independent, right? Again,
yeah.
Scheme dependent.
Yeah, that is scheme dependent. Yeah. Yeah, that's, yeah, I think the L hor is not so, yeah, in fact, they don't emphasize it, but they use this particular scheme. But we have actually kept the scheme all the time, and it always lands up into that. Yeah.
Function is unambiguous.
One.
Geodesic regularized length is
not, yeah, that's correct, yeah.
Scheme dependent.
Yeah, that's correct, yeah. Yeah, the 1 point function doesn't see anything of that kind. It just gives you this answer. Yeah. Radius of ADS.
Okay, but that we can set to 1, I guess.
Yeah, so it's pi by d.
So the expectation value is the farther dependent on Z naught, it just went into the real part. You're saying that way the farther dependent on the
Yeah, the Z naught does not play a role here. Yeah, it's a ADS sort of feature. You can do this integral. Yeah, okay, yeah. Something which looks like 1, and some other number which looks like 1. Yeah. So what is the motivation for saying that these things are the same, right? Because they're not even able to match the log 4. Right. Yeah. So we do other examples. Let's do other examples. Interesting is if you took a black hole form from collapse, right? Look at the case where the horizon to singularity time is actually changing with time. Okay. If you prefer the 1 point function at the same time. Yeah. That would be something. Yeah. So here now I'm going to do a 1 point function with inner horizon, and there will be another length. So we'll see how the other length comes in. That will have the charge dependence. let's see that.
Justin, I have another question. Like, is there any way to compute the one-point function in the field theory itself, on the boundary itself?
Yeah, so that's what our next motivation was, and I will go towards that, towards the end.
I see.
But we wouldn't do it like, you know, this we need one, we will do it strictly at large n and strictly at large lambda. So we would
of course.
interesting result. We would get some results, but we wouldn't get as interesting as this one, actually. Yeah, because
no, but shouldn't they ultimately shouldn't they match?
Yes, they should actually. I mean, that is the thing. If you can do this powerfully, if you can do it carefully in CFT, I mean, if you are able to do this, you are supposed to see this feature, which has this nice phase and some length of this kind. You're supposed to see it. Yeah, it's true actually. So that's what motivated us for the next calculation. I will see how far. I mean, I don't know whether I'll reach there even. Yeah, so this is the rough scheme of things. This is the length and this is the other one. Now, let's look at the charged planar black hole. Now, this black hole has an inner horizon, right? So there is, you know, there are two horizons here now. So there's another horizon. Okay. And let's go ahead. So there are three, sort of putatively three invariant lengths. L hor, the distance from, you know, from the from this to the outer horizon to the boundary, the proper time from inside to the outer horizon to the inner horizon, as well as the proper length from inner horizon to the singularity. So there are three lengths now. And yeah, this is the structure of the three lengths. You know, Maldacen and Grinberg, right? They attempt to do that. I mean, they do, I guess, in their way, the one-point functions, but they do WKB analysis. And you know, there's a lot of arguments to choose the saddle point, and in fact, there's a complex saddle point, and so on. But we will just proceed straight away. Okay. So we have to look at the minimally coupled scalar equation in this background, and it is this, right?
Which part is the WKB done? Which part of the calculation that you should?
The WKB is done because, I mean, they think of this, one-point function. The one-point function is like, it's some exponential of an action, of a geodesic action. Yeah, so they argue like that, and there's a sort of saddle point analysis for those things, and yeah. It's quite involved, and it's very Maldacenish, I should say. Yeah, right, yeah. Had saddle point, yeah. It's hard to follow, actually, you can see it. But here we just look at the minimally coupled scalar equation, this is the sort of equation. Of course, it's, we have said this, and it's hard to solve. Of course, it's hard to solve. That was the problem. Uncharged scalar. Now, this equation is not solvable in a simple analytic function. But if you take the following large D limit, okay, so D goes to infinity with this particular combination held fixed. Okay. You see the structures are here, and if you hold it of this kind, if this particular held fixed, then the equation reduces to this following form. Huh?
CFT dimensions.
Yeah, CFT dimensions. Large D analysis. So in the bulk also it's large D analysis. But it's not, I mean, most probably, we try to compare with the Shiraz's large D, it's not that kind. Because the horizons are intact. You'll see the horizons are intact. So you take the large D analysis, large D limit, and this is the equation.
But it's probably also true that just outside you get ADS, right?
The solution, actually, I'll tell you the solution. The solution is basically this combination. This is like Z by Z naught. You see, Z by Z naught to the power D is W. Okay, and if you take this particular limit, okay, I will show you. It just becomes W squared. So the blackening factor is a very special form of the blackening factor. And we have rechecked. Actually, we took that limited solution and plugged it back inside. It becomes ADS at boundary also. It doesn't very quickly fall to ADS. But if you plug it inside the Einstein's equation, the large D, the corrections to the Einstein's equation is exponentially in D. So that's how it solves the answer. We have checked how it solves the Einstein's equation. So this radial equation becomes of this kind, and here it is. Here is the blackening factor. You see QW squared, and it becomes this. And the inner and indeed it admits an inner and outer horizon of this kind. Okay. So this is what I was saying, that with this blackening factor, the solution satisfies Einstein's equations in the large D limit with corrections as exponential in D. And we can actually, with that solution, because I said the equations are solvable, we can actually solve for the bulk boundary Green's function. Okay, it is this. It's a more complicated structure, but the structure and we can evaluate the Gauss-Bonnet and take its large D limit. Okay, it is of this kind, and substitute in the 1-point function. Okay, and see the integral again is 0 to W out, meaning from here to here. That's the integral. Yes.
One question I had about the Greenberg analysis: if you have a charge band, why can't you have contributions from things like phi f squared?
Phi f squared, yeah, you could. I mean, yeah, phi f squared, yeah, such things are there. But
f squared is non-zero in the natural.
Yeah, yeah,
so
that.
Connect any? I mean, it connect the 1-point.
Yeah, that will have, of course, a charge kind of term in front. I mean, yeah, it's.
No, you know, uncharged phi.
Phi f squared, yeah.
Yeah, I'm not talking about charge phi.
Yeah, yeah, it will have a charge of the black hole in front. I mean, because F goes as charge squared. Yeah, so it will have some. I mean, we haven't evaluated that one. I mean, yeah, 1-point functions with that kind, but that will have a slight different structure. Yeah, we haven't.
It won't change the solution that you have.
Yeah.
Right. It will just change the onshell action.
Onshell action.
You just add to Gauss-Bonnet.
Right. It's probably doable. Yeah. So so again, we sort of integrate it from 0 to W, and you can see that the integral is from outside, and we have. I mean, there's a small check. You can show it reduces to the uncharged case, and the integral can be evaluated. And again, you see that same structure coming out, 1 by sine pi h coming, and this is the integral. I mean, there are two terms. Okay, and we are instructed to take the large H limit here. And you can do that using Watson's approximation. I mean, Watson has a method of like taking the large orders of the height, because you see orders are coming here, and you can do it. You can take the large H limit, and this is the structure you get. So there is more structure to it now. There is this term, there is this arc secant time, and then there is that e to the minus 5 phase with all those things and powers of h. So this is the large H limit of that 1-point function. And now let us compare it with geometric lengths again, right? So here it is. This is the proper time. And again, take large D. And that is indeed just pi r by d. Yeah? It's surprising that that's also pi r by d. And between the inner and the outer horizon. You evaluate the proper length, again with the same kind of regularization. This might be sort of suspicious, but you get this structure, and that's the L HOR, and you can see that structure is there, like the 4 divided by 1 minus 4q. It was log 4. Yeah, sec 1 is basically from inner to the singularity, and if you do that, yeah, the sec winds up. The distance from here to here comes. Yeah. Yeah.
This is a little confusing.
Yeah.
Because the 1-point function is a real black hole.
Right. Yeah. Right.
The inner horizon itself is the singularity. You don't expect there's a.
Yeah. So, but that's what is surprising, yeah, because the integral is evaluated completely here. The integral is completely evaluated here. Then there's a large H analysis, which gives you all this.
It is just a mathematical identity, right? I mean, it's not just.
Yeah.
There need not be something.
Deep. Yeah. Yeah, it's somehow mathematically it has come. Yeah, it has resulted in this. Yeah, yeah. Yeah. So you okay? You evaluate this length.
It's not a length because the singularity is.
So it's this. Okay, if you want it in Penrose diagram, it's this. L Hor is this, and this is L Sing, and this is the tau. Yeah. It's space. Yeah.
That's not a geodesic of any particle.
Yeah, it is the proper length. I mean, yeah.
Not the proper diagram.
Yeah.
But even the shortest
Yeah. Yeah. L Hor was just the integral. This is actually the length. If you drop a particle from here to here, this is actually the length. Yeah.
And what you would have thought is that length is the only physical length.
It's this one.
Is some mathematical.
Yeah, yeah.
But do you see the tau in the 1 point function, or do you see LC?
You see tau in, I see this, all three.
LC plus L.
Yeah. It comes in a combination. Oh, wait. Let me write it. I'll show you the combination. Yeah. This is the combination it comes in. L Hor plus L Sing minus I tau S. Yeah. So this is the generic structure. Yeah.
It's a bit scheme dependent.
Yeah, yeah. It's a bit scheme dependent. Yeah. This part is a bit scheme dependent. The phase is always the sort of the physical length, which is the geodesic length, comes out as a phase all the time. Yeah.
That's the length of the outer to the inner.
L Sing. Tau S. Yeah. Tau S. That's the only physical length, and that comes out correctly. Yeah, that comes out correctly. Yeah, scheme. Yeah. But it sort of naturally comes out with it. Yeah. This function comes out and so on. Yeah.
All the edge dependence and so on is in L.
Yeah.
So tau is just 1 over d again.
Again, yeah. In this limit for us, in this particular limit. Yeah. Other terms. Yeah. But still, it lands up.
Tau just depends on a dimension.
Yeah.
That means you can take an inner horizon, and you can move the inner horizon and make it to 0, right? I mean, vanish in the end, right?
Yeah, that's what happens in the Schwarzschild case. There is no inner horizon. Yeah. So let's see now. There's one more example. The hyperbolic black holes. Yeah. There's one more example. So here you will see that again. So you consider the hyperbolic black hole, right, in ADS. And so this is a black hole whose boundary theory lies on r times ADS d minus 1. There is a particular slicing of ADS basically. So there is a horizon. It admits a horizon. Okay, and
You can have a 1 over d expansion.
I don't know 1 over d because it's exponential. The corrections are exponential.
No, but let's see the Gauss-Bonnet correction.
That is a 1 over d actually. Yeah, that's a 1 over d. Yeah.
So those will be.
This is a leading term in the Gauss-Bonnet.
Let's say we ignore all the conservative.
Yeah. D to the 4 by
Yeah, but here can you get the 1 over d correction?
I don't know. Yeah, we haven't done it, but there is this this term. It will come as a log W. We haven't done it. Yeah, we have done it. Yeah.
The whole analysis works if one tries to take the extreme limit also.
Extremal limit. Yeah, I don't know. We haven't done it. Extremal limit. Yeah. That's a little tricky actually. Extremal limit. Angular momentum, I will tell you. Yeah, we tried quite a bit in the real higher dimensional black holes, angular momentum, but we didn't. We were not able to solve you need to solve the equations exactly for these things. We couldn't solve the equations. We tried quite a bit actually, angular momentum. Yes.
Because analytic continuation you can't do.
And you can't do analytic continuation by numerics. Yeah, and you need these exact forms. I mean, it's very. Yeah, the integrals are naturally just diverging. You need the answer, somehow you need the answer, and then you have to analytically continue it.
Because the 1 point function you're saying is not right.
Well, it's well defined for small h.
I understand.
Yeah. When you just want to do the integral by hand, I mean by numerics. There should be. Yeah, there should be a way. Yeah, there should be a way. Yeah. There should be some prescription, but yeah, we have to work on that. Yeah. So let's go to this one. This is another example. So that is even everything is slightly different here. So this is a hyperbolic black hole, and there is this there's a blackening factor here too. There's the CFT is on a hyperbolic space actually, and hyperbolic space times R, which is compact for a finite temperature, and there is this temperature, and it is dual to this particular case. I mean, conformal field theory is it's supposed to be dual on this, and there is a Gauss-Bonnet, and in this case, the Gauss-Bonnet, of course, because it's pure ADS, it's just constant, and you can again try to do the same thing. You can decompose you try to solve the bulk Green's function and evaluate the bulk boundary Green's function. You do mode by mode actually, and using various symmetries, you can set angular momentum on those spheres. Because it's ADS d minus 1 here times R. That's the boundary. So there is a radial direction here itself, and then there is a sphere. And the sphere angular momentum can be set to 0, and you need to solve this sort of equation, which is solvable again. Which is solvable. Lambda is, so when you decompose into modes, I will write it in the next, when you decompose it into modes, there is the harmonics on the sphere, as well as that, the harmonics, the Camporesi-Higuchi harmonic, or the harmonic on ADS. So we decompose the Green's function like that, and all the rest can be set to 0. The harmonics on ADS lambda just stays, because we are looking for the constant mode, and like constant integral to that harmonic is not 0, unlike like the other ones. Like angular momentum modes on a constant, when you integrate on a sphere, it picks out only the 0 mode and so on. So this one, we have to keep that. But finally, it will turn out all. Oh, it went away. Yeah. So the thing is that now the tau s and all the structures are slightly different. And again, it has that same property. Yeah.
So your calculation actually is in
Euclidean space. Yeah.
Why would that have this type of information?
Yeah, that's.
Which is,
beyond
the horizon.
Yeah.
Thinking, or this is just numerical?
Yeah, not numerical. It's analytical, analytical formula. Numbers. Yeah.
Is there some intuition?
Yeah, so Maldacen and all have some intuition in the sense that they argue using WKB, and somehow they say that the saddle point geodesic somehow goes inside. Somehow it sees that in the complex domain. So they go into the, the WKB goes into complex. Yeah, Euclidean picture, there's no inside. Yeah. Yeah. There's no horizon.
How does it know?
Yeah.
When you do the saddle point, somehow the saddle point doesn't give you the Euclidean picture, but somehow you do
Yeah. Lorentz, yeah, it is a complex saddle actually. It's a complex saddle.
Shankar et al. Story of looking at these geodesics,
right? Yeah. I think this calculation, that is a 2-point function, and this is a 1-point function, which is
The point is that even the Euclidean partition is communicated by the Lorentz
saddle.
Somehow, but I'm not understood. It seems to me that is not completely.
Yeah. So here, of course, we don't. We just sort of. It's quite straight. In the sense. That's why, like Maldacena has all those WKB approximations and so on, but this is a little bit more linear in the sense that we can just do it. Okay, so it hides the physical fact, but the calculations are linear. Yeah. So we do this. So lambda is the the eigenmodes on the ADS, and again the 1-point function can be evaluated with some structure of the gamma functions, something. You can see the correct dimensions and all come out. And if you take the large lambda limit, large delta limit, again that 1 by sine kind of structure comes. But this is pi delta by 2 now, right? It's always like this. In any dimension, it's pi delta by 2. And again, there is this delta log 2, powers of delta. But this is it's a different structure. So if you use delta as mr and write it out, it's of this kind, pi r by 2 minus r. So it's different from before. In a general D, yes, general D still it is independent. It's a different dependence here. Again, comparison with geometric lengths, you get the same tau s, which is expected from the 1-point function. And yeah. Yeah, it's m minus mr is there. That's the delta.
So the phase basically you're saying is always I pi m as a 1 point.
No, I pi tau s. I m tau s. Yeah, tau s. Pi by d, pi by 2. Here it is not 1 by d, it is just pi by 2.
This is for all d.
Yeah, this is for all d, yes. Yeah, for the hyperbolic black holes. 1 by 2. Yeah. So it agrees, and even that with the regularization, yeah, if you're taking the same kind of regularization, it agrees. The L-Hor also agrees. So
these kinds are arguing the same way as the WK thing.
I don't know actually. Yeah, so we haven't like examined the Maldacena WKB picture here actually. Yeah.
But for hyperbolic black holes, I mean, the charged black hole had a lot of transcripts.
They had to do weird stuff for the charged black holes. Yeah.
But this should be like a Schwarzschild.
This is a Schwarzschild version of it. Yeah.
But Greenberg constants, so there the standard point analysis should be simpler.
It should be simpler, but we haven't. We haven't done it actually. We were more interested in trying to study it in field theory, so that's how we went in the next direction actually. Yeah. I don't think I will reach there. But I should just say remarks about 2 and the thing about rotating black holes. So in 2 dimensions, Gauss-Bonnet, Weyl Tensor, all these vanish. They vanish, right? And therefore, I mean, it is indeed consistent with the fact that if you have 2D CFT on a line, 1-point functions don't get, for primaries, they don't get expectation values, right? Because you make a conformal transformation from the plane to the cylinder, and then you don't get. But if it's on a torus, they do get expectation value. And I think this is Maldacena and Greenberg, they show that on a torus, the same structure occurs, but it's suppressed by the size of, size of the spatial size by beta. So therefore, when the spatial size is infinity, you can see it vanishes. Now, we have tried to do this for the rotating black hole. We did it for the rotating black hole because they did it for the Schwarzschild, I mean the BTZ without rotation. We did it for the BTZ with rotation because this is quite a solvable thing. And we didn't find that inner horizon structure. We just found the same structure actually again. For the rotating case, we didn't see that structure. But we had to take certain limits because already this is under some limit and so on. So maybe this limit washes out that thing. We don't know. So it's a little ambiguous. I mean, so the thing about rotation is that we tried in higher dimensions. We couldn't solve the equations. We looked at 2D, and we had to take certain limits because already it vanishes, and so it's not very clear that we are seeing any features. So I'll stop now, and this is the holographic calculation, and of course the next motivation was because it was such a clean calculation in holography. We thought, okay, let's see in CFT whether we can see any features. Now in CFT. The thing is that, of course, there are very few solvable models, and we straight away went to this large N ON models and so on. So we saw there is a sort of universal feature in this 1-point function, and can we see this in CFT? And the 1-point functions, as we saw, they are due to this higher derivative term, and therefore we need at least the first order correction in 't-Hooft coupling, but let us see at large N and large coupling, whether we can see any features at all. Now, the class of models we studied is the ON model, and the Gross-Neveu model. So these two models. And we are not, we are studying primaries, but these higher spin objects. These objects. So they are different class altogether, but these are the things which could handle, have a handle on. They are these structures. And they are symmetric traceless tensors, and L equals 2 is the stress tensor here. And the strategy to obtain one-point functions is basically, it was introduced for the bosonic fields first by these authors, and it was applied to the ON model. And we have extended the model, this method, to fermions. There was a minor extension by Petku and this in 2018, but they looked at a specific class of one-point functions. This one is a little general, and it sort of handles it a little generally. And in fact, they don't consider the class which has the stress tensor. So the method, should I say the method, or I'll just go to because the method involves quite a bit of sort of technical thing. I mean, the method, maybe I'll just briefly tell. So the method is essentially, we look at OP, so I'm showing it to the bosons. So we look at the OP of two bosonic operators. It's of this structure, right? And then we take expectation value in the thermal state. So we get, on this side, we get one-point functions, right? A simple strategy, actually. And then somehow we need to invert. Given the two-point functions, given the thermal two-point functions, we somehow need to find inverse to read out these one-point functions. Now, again, using translation invariance and rotational invariance, it's only the time components which get expectation values, actually. And then there is this coefficient which we are after. Okay. So this expectation values are of this form, just from translation invariance and so on. It's of this form. And when you plug these structures inside here, inside this, you get certain Gegenbauer polynomials and so on. And this is the expansion of the two-point function in terms of one-point functions here. And this expression you can invert. And that is what they call the Euclidean inversion formula. Maybe I can, since in the lack of time, what I will do is I'll just I won't go through the rough derivation of the Euclidean inversion formula. There's a formula in which you can actually, sort of invert for the one-point functions of all the higher spin operators from the two-point functions. Okay. Is that okay? Because if I go through the analysis of the thing, because I wouldn't, I have 15 minutes. Maybe if we have time, we can go through this analysis. But right now, let us just take that there is a two-point function, and we can find the one-point functions from there using the Euclidean inversion formula. Now, this is all the inversion formula. Right. Now, the ON model, the two-point functions are known. This is the two-point function. For instance, this is in 3 dimensions. This is known, but in terms of the thermal mass. So there's a thermal mass, and then there's the two-point functions known. This is the two-point function, and then you can use that inversion formula and read out the one-point functions. And here it is. And the thermal mass is read out from the gap equation, and the gap equation itself has a way of doing it. Like, we just demand this expectation value of phi squared. Because we can extract the expectation value of any of these composites, we demand the expectation value of phi squared vanishes. And that results in the gap equation of the ON model. And we have checked that it is indeed, we take the partition function and do the Hubble-Stratonovich, verify that indeed that expectation value of phi squared vanishes. And that's the... yeah, that's right, yeah. And then this is the gap equation. And we have the expectation value of one-point functions. And also we do, for instance, this is a solution. So the interesting thing about this ON model is that, the gap equation has positive real solutions in these dimensions, right? In these dimensions. And there is no real solutions for these dimensions. This phenomena was noticed earlier, actually, by these authors. And here we see that in evidence. This is in D equals 3. The gap equation has a solution. There are no solutions in higher dimensions. And we do a consistency check that we look at the spin 2 current in 2 ways, from the Euclidean inversion formula and from the partition function. And with the gap equation, they coincide. Okay. And this is the ratio. This is the universal thing. It is not as interesting as the black hole, but still, but we study the ratio of the one-point functions at the non-trivial MTH, right? At the non-trivial fixed point towards the with the Gaussian fixed point. Okay. And we examine it in the two cases. Keeping as you increase dimensions, and as you keeping the spin fixed, and as you increase the spin. We examine it in two cases. So if you increase dimensions, this ratio decreases to 0. Right. So you look at this ratio of one-point function, and it's going to 0. Huh? I don't. Well, yeah, I don't know. We didn't fit it actually. Yeah. 1 by d. We didn't. Yeah, I know. We didn't. Sorry, we didn't fit it. Yeah, we didn't check actually. We are trying to do it analytically now actually, and figure out exactly this structure of this form. So as you increase the dimension, this ratio of one-point functions reduced to 0. Now we actually, if you think about it, it looks like the degrees of freedom decreases at the non-trivial fixed point more and more as the dimensions increase, which is similar to what many people are saying in CFTs. Somehow there is no non-trivial CFT in higher dimensions. But but we check it also with the stress tensor, because the coefficients of the stress tensor, the front, which is there in terms of the Boltzmann term, no? That coefficient gives a measure of degrees of freedom. And if we can read out that also. And we can read out that, and the free theory, like it becomes this, and the critical theory just goes down.
They're all real?
They're all real, yeah. They're all real, yeah.
So, but the point is that, at large h, you got some.
Oh, that is that one. Yeah, that is actually, it was real only. It was just that extraction of the e to the power of I. It was real only, yeah. Yeah, it was 1 by sine pi. 1 by sine pi h, yeah. So and on increasing L, it actually becomes like the free theory, right? The ratio becomes more and more Boltzmann-like. Yeah.
1 by sine pi, if you want to write it as little minus alpha.
Yeah, there is this infinite set of terms, yeah. With an I epsilon. Yeah.
It makes sense if h itself is taken to be
slightly imaginary. That's what they do. Yeah. Yeah. Epsilon, yeah. So so that degrees. I mean, the energy density also shows the same feature, that somehow the degrees of freedom are decreasing, and the ratio on increasing spin at a fixed dimension. This happens even in, say, in 3 dimensions. It becomes unity. So it becomes more and more free-like when you increase this spin. Yeah. Yeah. Delta. It could be, yeah, because it's very general actually. It's very algebraic. I mean, very algebraic. Maybe, we haven't looked at it, but we can, indeed.
There is probably be no
black hole. At one, that's what we thought. We don't have black hole. That's one of the features. But this is what was tractable. I mean, but we could do this at 1 by. That's what we are thinking. We could do this at 1 by root lambda, the first correction, because the gap equation can be corrected to first, and see whether that one has. Most likely it doesn't, but has these kind of dependence. I mean, like this is leading order in N and leading order in strong coupling. But one could do this. It's reasonably not difficult actually to do the 1 by root lambda, 1 by drift coupling correction to this. Yeah, if it has the similar structures as what we saw in the. Yeah, that kind of structure. Some structures of that kind. Exactly. I mean, unlikely, but I mean, it's worth a try, which we might try actually. So
another question. Is a lot of question in the black hole tractable, like having highest particles?
There is some solution actually. There is a written down solution by Vasiliev. Yeah, the 2-dimension is always some bad guy for this kind of things actually. Yeah.
But in higher dimensions, probably even spin guys have 1.5.
Yeah, these are even spin. All of these are even spin. Yeah, these are even spin. Yeah.
And you could couple even spin guys to
some. So okay, anyway, we are coming close. So we do it again for the Gross-Neveu model. So we developed the Euclidean inversion formula for these fermions, which was not there in the literature, and we have to look at it's slightly more complex. So there are these operators of this kind, like gamma with the dels, and the ones ones with these contracted. They somehow mix, and we need to decouple them, and we can do that. And we have the correlator 2-point function is known, and we can read out the 1-point functions again, and even spins get expectation values. And the gap equation is obtained again by the expectation value of psi bar psi is 0. We have cross-checked that with the Hubbard-Stratton saddle point, and that's the gap equation. And it has solutions in the opposite, like in D equal. So in D equals 3, it doesn't have solutions. D equals 5, it has solutions, and so on. It has certain solutions. And we have also verified that the spin 2 is proportional to the stress tensor. Once substituting the gap equation. Since we did this fermions first, so we did an exhaustive check about that. Here is the spin 2 thing, and this is stress tensor, and up to some definitions, it's the same. Yeah, these are large numbers. Yeah. Because, I guess this, 2 to the k, because there is 2 to the k, fermions. The fermion multiplet is 2 to the k, roughly, right? 2 to the k is the dimension. Yeah, d is equal to 2k plus 1. 2k plus 1. Yeah. Yeah. So, but this is just you can scale it out actually. This is just some. This one. This is the stress tensor evaluated from the partition function.
Just because I
say
that 2 to the
k components are there. Yeah. You can see it here. But here also, after some time, it increases. Yeah.
But
2 to the k.
The 1-point functions also grow.
The 1-point functions grow. Yeah. So again, we evaluate these ratios, and exactly the same behavior as in the one model. At large k, these things decrease, and the degrees of freedom reduce in large k, and together, also it becomes free at large L, large spins. It becomes as though it's a free model. Yeah. So these are the universalities, but of course, our goal was indeed to find something like the black hole behavior. But this is what we could extract at this stage. But we are looking at this problem still in the field theory. There's no black hole, yeah. But we wanted, of course, this was a starting point for some field theory to study this. We hope that, with the 1/λ, I don't know whether it will be there or not, but most likely not. But still, these are something which we can, most likely not, actually. But still, it's worth looking at the first order correction to this thing. Because the black hole, that 1-point function. Yeah, I think there is a black hole solution for the Vasiliev theory, but it's very it's a mess. I think, it's a mess.
Try this for Jones.
So that's an open problem in this actually, because this gap equation is not easy to implement. Like how to implement it in the OPE inversion formula is not, because there is an integral over the holonomies. So that is not like how to improve. We looked at it for a while and we thought we had the answer, but we don't have the answer actually. Yeah. So we are studying something close to that, things with chemical potential. This is close to that, but not quite exactly the Chern-Simons model. Yeah, but that's an open problem in this OP inversion thing. To use the because as far as you know, the 2-point function is known. The exact 2-point function is known. It's a matter of like doing that holonomic correctly and inverting it. And yeah. We could do it actually. Yeah. So the polylog functions have the chemical potential. It just assembles itself correctly into that actually. Yeah, fugacity. Yeah. Okay, so yeah, that's what we have done. Okay, thanks. Many questions were asked. Yeah, it is certainly it'll be very good if we can actually, from the field theory, we can see this. So of course, that's what many people want to do, to see some signature of the black hole. I think,
There are no questions. Let's just come to
Thanks, Justin. Very interesting.